In the world of IT, data is king. It forms the backbone of our understanding and drives the quest for innovation. Every piece of data collected has the potential to unlock new insights and advancements. We gather vast amounts of information, but raw data alone doesn't tell us much. It's like having all the pieces of a puzzle but no picture to guide you. Without proper analysis, data remains just numbers and figures. This is where inferential statistics come in. They are the bridge between raw data and meaningful insights. By applying statistical methods, we can interpret data, identify patterns, and make predictions. Inferential statistics are the tools that allow us to make sense of data, draw meaningful conclusions, and generalize findings from a sample to a larger population. They help us move from observation to understanding.
Imagine wanting to know if a new software feature is effective. It's not enough to see a few positive results. We need to know if these results are consistent and reliable. Inferential statistics help us determine if observed differences between a group using the new feature and a control group are statistically significant or merely due to chance. This distinction is crucial for making informed decisions about the feature's efficacy.
Inferential statistics are crucial for making informed decisions in various fields. From software development to business strategy, these statistical methods provide the foundation for evidence-based practices. In software development, for instance, understanding relationships between variables can help in optimizing performance. In business, analyzing performance data can lead to improved strategies. Whether we're studying the effectiveness of a new software feature or the impact of marketing campaigns, inferential statistics provide the framework for robust analysis. They enable us to make predictions, test hypotheses, and ultimately make better decisions based on data. By leveraging the power of inferential statistics, we can transform raw data into actionable insights, driving progress and innovation across various domains. The ability to infer and predict from data is what propels us forward in our quest for knowledge and improvement.
Let's say we're interested in comparing the effectiveness of 3 different teaching methods on student performance. Imagine we have 3 groups of students, each group being taught using a different method. The first group uses traditional lectures, the second group uses interactive activities, and the third group uses a blended approach, combining both lectures and activities. We could collect data on student scores after being taught using each method. This data would give us an idea of how well students performed under each teaching method. For instance, we might administer a standardized test to all students at the end of the teaching period and record their scores. But how do we know if the observed differences in average scores are meaningful or just random variation? It's possible that any differences we see are just due to chance. This is a common challenge in research, where we need to distinguish between real effects and random noise. This is where one-way ANOVA comes in. One-way ANOVA, or analysis of variance, is a powerful statistical tool that helps us determine whether the differences in our data are statistically significant. It essentially compares the means of our groups and tells us if at least one group is different from the others.
One-way ANOVA is a statistical test used to compare the means of 3 or more independent groups. It's particularly useful when we have multiple groups and we want to see if there's a significant difference among them. For example, in our teaching methods scenario, we want to know if the teaching method has a significant impact on student performance. It helps determine if there's a statistically significant difference between the group means. If the ANOVA test shows a significant result, it means that at least one of the teaching methods leads to different student performance compared to the others.
In our teaching methods example, one-way ANOVA would tell us if one or more teaching methods lead to significantly different student performance compared to the others. This information is crucial for educators and researchers as it helps them understand which teaching method might be more effective.
If the one-way ANOVA indicates a significant difference, we know that at least one group mean is different from the others. This is a good starting point, but it doesn't give us the complete picture. However, it doesn't tell us which specific groups differ. To find out which groups are different, we need to conduct further analysis. To pinpoint these differences, we need to conduct what are known as post hoc tests, which we'll delve into in a later section. Post hoc tests help us identify exactly which groups are different from each other, providing a more detailed understanding of our data.
Now, let's imagine we want to explore the effects of both teaching method and student gender on performance. This is a common scenario in educational research where we aim to understand how different variables interact to influence outcomes. We suspect that certain teaching methods might be more effective for one gender than the other. For example, collaborative learning might benefit female students more, while competitive learning could be more effective for male students. In such cases, we need a more sophisticated tool two-way, ANOVA. This statistical method helps us to not only look at the individual effects of each variable, but also how they interact with each other.
Two-way ANOVA allows us to examine the main effects of two independent variables, in our case teaching method and gender. The main effects tell us how each variable independently affects the outcome, and crucially, their interaction effect. The interaction effect is particularly important because it reveals whether the effect of one variable changes depending on the level of the other variable. The interaction effect tells us if the impact of one variable depends on the level of the other. For instance, the effectiveness of a teaching method might vary significantly between male and female students.
For instance, we might find that one teaching method is particularly effective for female students. This could be due to various factors such as learning styles, classroom dynamics, or even societal influences, while another works best for male students. Understanding these nuances can help educators tailor their teaching strategies to better meet the needs of all students.
By considering both main and interaction effects, we can gain a deeper insight into the data. This approach allows us to see the bigger picture and understand the complexities of the relationships between variables. Two-way ANOVA provides a more nuanced understanding of complex relationships between variables. It helps us to identify patterns and trends that might not be apparent when looking at variables in isolation. It allows us to move beyond simply looking at individual factors in isolation and delve into how they might influence each other. This comprehensive approach is essential for making informed decisions and developing effective strategies in various fields, from education to business and beyond.